I feel like I shouldn't even make this video. Okay, so in case you haven't seen the news, there was a politician that said, hey, climate change, what if we just moved the Earth? Problem solved, right? If you move the Earth further away from the sun, it won't get so hot and you guys can fix the problem. I mean, no. So, but it's still a good place to do a physics problem. So let's do a physics problem. Let's see. One, what would happen if you move the Earth further away? What would happen to the solar irradiance, which I'm going to call it the intensity? And then how much energy would it take to move the Earth? And then let's just see what happens. Because I don't know what's going to happen. I haven't done the calculations yet. Okay, so let me turn off this camera and just get to the paper. Okay, so here we have the sun. And here is the Earth orbiting. And this is not to scale, just so you know. And the sun has, it's nuclear fusion. It radiates energy in uniformly in spherical directions. And at the location of the Earth, I looked this up, the intensity of light is 1,361 to 1,362 watts per square meter. And I think that's at the upper atmosphere. So that doesn't include what gets down to the surface of the Earth. But that's the energy, that's essentially the power per area that hits the Earth. And so this is a great thing to use as a metric for how much solar energy we get from the Earth, right? And so some of this solar energy radiates down, hits the surface of the Earth, warms up the Earth, that re-radiates carbon dioxide and water vapor in the atmosphere are greenhouse gases in that they reflect that back down on the Earth and they trap it and it keeps the Earth warmer than it should be. Too much carbon dioxide and it warms up too much, which can produce more carbon dioxide. And so it's a carbon dioxide problem. And so instead of fixing the carbon dioxide problem, the idea is, well, what if I move the Earth over here to some other distance? And I'm going to pick a value. Let's do this. Let's pick. I want to calculate how far I need to be to reduce this by 1%. 1% reduction in intensity, and then we'll find out how much energy that is. So that's the first question is, so I want to go, let's go from, I wanted to say let's call it I new, is going to be 0.99 times 1361 watts per square meter. So where would I have to be in order to get to that intensity? That's the first question. So let's think about it this way. Let's say the intensity is PO divided by area, right? That's the power per unit area, and this is PO, the power of the sun. And if I know the distance to the Earth, that power is radiated uniformly over a sphere, and I know that the area of a sphere is 4 pi r squared. So this is going to be PO over 4 pi, and I'm going to call this RE, the orbital radius of the Earth. Not the radius of the Earth, it's the orbital radius, how far the orbit is, and that's 1 AU, and I can look that up. So 1 AU is equal to the orbital radius of the Earth. And that's an AU is an astronomical unit. We define that. Now, I should point out that the Earth's orbit around the Earth is not circular. It's close to circular, but it's not. So we're actually further away in the summer for the northern hemisphere a little bit than in the northern hemisphere. And so actually we're warmer in the summer because the northern hemisphere is tilted towards the sun, and that gives a higher solar flux because the sun's higher in the sky and in the sky for a longer time. Where was I? Okay, so I can solve this for, let's call this IE. I know that value, and that we can solve this for PO, the power of the sun. So PO is going to be equal to the intensity at the Earth, and I'm going to use that value right there. This is my actual intensity at the Earth, times 4 pi times RE squared. And I know all those values. So I don't actually need to know the power of the sun, and you could look it up, but I don't want to look it up. Okay. So now, let's just check. What if I wanted to calculate the intensity at Mars, which I can actually look up? So the intensity at Mars is going to be equal to the PO divided by 4 pi times Rm, where this is the orbital radius of Mars. So I know, I looked this up, the orbital radius of Mars is 1.5 0.24 AU. So I can look up that value. And I'm going to plug this in the calculator in just a second. So I know PO is this. I can put that in. It's going to be IE, which I know, 4 pi RE squared over 4 pi RM squared. The 4 pi's cancel. And I get, this is going to be equal to the intensity of the radiation at the Earth times the radius of the Earth squared divided by the, that's right, that's squared, times the orbital radius of the moon, of Mars squared. And I looked this up. This should be 590 watts per meter squared. Okay, so let's switch over and just check and see if this is working. So I've already got some numbers entered into my my Python calculator. Let's make this a little bit bigger. Oh, let's see. Oh, that's a little bit too big. Well, that's fine. Okay, so I already ran it once. So here is my intensity at the Earth. I put that at, let's put this at 1. That's the expected, that's what I've looked up as the intensity at the solar, and it's solar irradiance, which I call the intensity, is watts per meter squared on Mars. Here's the orbital radius of the Earth. That's, I put it in AU. This is the orbital radius of Mars, multiplied by AU. G, I'll need that later. Mass of the sun, mass of Earth, I actually need that in just a little bit. So let's say, we can do it either way. I can say PO equals, just like I said, it's going to be equal to IE times 4 times pi times RE squared. And then I can say IMM, I'm going to give it a different name. That's the intensity at Mars. It's going to be equal to it's going to be actually just PO, which I just calculated. This is what's so great about Python. I don't have to solve for stuff. Times 4 times pi times RM squared, and let's print that. This is lowercase. Print IMM. And I get 585. So I'm pretty happy with that. It seems like it's working. Okay. So now let's go back and find out the orbital radius for the Earth. So I'm going to switch back over here. Okay, the orbital radius for the new Earth. So let's call this like this. There's my sun. There's the old Earth. And there's the new one. And we'll call this RE2, the new orbital radius of the Earth. So I want IE2, I use capital 2, is going to be 0.99 IE. And that's going to be equal to PO divided by 4 pi RE2 squared. So I just need to solve this for RE2 squared. So RE2 squared is going to be PO divided by 4 pi times 0.99 IE. And then so actually I define PO in terms of IE, but I don't really care because I've already got a calculation for PO. So let's see how far this would be. This would be RE. It's going to be the square root of PO, which I already know. I never even wrote it down. 4 pi times 0.99 IE. Okay, let's switch back over to Python and get a value for this. Yes, I'm switching back and forth. I can do that. Okay, so let's just do this. IE2 equals 0.99 times IE. And then RE2 equals the square, someone's complained about that. I gotta put spaces. Square root, I'm just gonna type it in here, PO divided by 4 times pi times IE. And print, let's say RE2 equals, because I got two things up here. Let's print this. I Mars equals, and let's put it all nice. Let's put it nicely. Watts per meter squared. And then down here, I'm going to say RE2 in meters. Let's put it in AU, right? Because that makes sense, because then we can see what kind of percent increase it is. Because remember, the Earth is right now at 1 AU. So let's print RE2 equals RE2 divided by AU. and that will be in AU. Okay, let's run it. And I got an error. RE2. I didn't put a comma right there. Okay. Oh, it's the same thing. It's not this. It can't be the same thing. So 4.196. What did I do wrong? Oh, I didn't do the 0.99. I forgot the 0.99. 0.99 times. Okay. Whew. Okay, so we're talking going from, we're increasing this by 0.5%. A 0.5% increase in orbital distance. Okay, now I want to see how much energy it would take to move the Earth that much further away. So let's go back to the paper. Okay, so if I have my system of the Earth plus the Sun, then I can say work equals the change in kinetic energy plus the change in gravitational potential energy. So we can define kinetic energy as 1/2 mv squared, and the gravitational potential would be negative g mass of the Sun, this is mass of the Earth, mass of the Sun, mass of the Earth over r. So if I want to move it from here to there, I'm actually going to have to add energy. I need to find the new kinetic energy, right? So right here, here's position 1, here's position 2. So I need to find the kinetic energy here, the kinetic energy there. I am going to have to change the kinetic energy. It's going to move at a different speed. And I'm thinking right now that it has to go faster, but I'm pretty sure it has to go faster. So let's just get a relationship for speed and distance, right? Because this actually all works out. So here is my gravitational force. The gravitational force is going to be the magnitude of g, mass of the Sun, mass of the Earth over r squared. And so if it's in a circular orbit, that force has to be equal to the mass of the Earth times v squared over r. That's the circular acceleration, is v squared over r. So I can use this to solve for v in terms of r. So the masses cancel. In order for being in a circular orbit, then v, let's just say v squared, because that's all I care about. V squared is going to be equal to g, mass of the Sun, and that r is going to cancel that over r. So I can get that to v1 is going to be that with r1, v2 squared is going to be g ms over r2. Okay, let's write down my... Now, I am going to have a change in energy. This whole change in energy, I need to find how much work it's going to take to change that energy. So let's say work equals, let's just write it out as K2 minus K1 plus U2 minus U1. So work, it's going to be K2 is 1/2 mass of the Earth V2 squared. But V2 squared is this. So it's going to be G mass of the Sun over R2 minus 1/2 mass of the Earth G mass of the Sun over R1, which I know that's when I'm starting. That's what I solved for with my other way. And now I have to do my potential plus the final potential. It's going to be negative G mass of the Sun, mass of the Earth over R2 plus minus a negative plus G mass of the Sun, mass of the Earth over R1. Now I can combine terms. Look, both of these terms are the same. I have 1/2 and I have the same thing but minus. So this is going to be equal to minus G mass of the Sun, mass of the Earth over 2 R2, right? Because it's 1/2. If I have that, yeah, that's right. And then this one's going to be minus, and it's going to be plus G mass of the Sun, mass of the Earth over 2R1. And that's going to be the work done. So I know the mass of the Sun, know the mass of the Earth, I know these distances, so I can plug this in to my equation and get the energy needed to change orbits. And this is true, this works for all circular orbits where you can combine the kinetic and potential energies. Okay, so back over to the computer. So I have RE2, I have RE1, and I have the mass of the Earth, I have the mass of the sun. So let's just, this is right out. Work equals, I'm just typing my equation. This was so great about Python, right? I mean, I know you think, hey, that guy's a crazy Python guy. Okay, that's true. I am kind of crazy Python guy. So minus G times mass of the sun. Oh, what I got to call it right? MS times ME divided by 2 times RE2 plus G times, I could have factored that out, MS times ME divided by 2 times RE. Print work equals W joules. Okay. 1.32 times 10 to the 31st joules. What's that? I was remembering that. Get rid of that. That's a lot. Okay, let's print out the power of the sun. PO, I calculated, I never printed it out. And then let's say if I get all of this from, and I capture all the energy from the sun, how long would it take the energy from the sun with a Dyson sphere? That's what a Dyson sphere is. It encloses all the whole sun, the whole star, and captures all that energy. If I use the power of the sun, how long would it take to move to this super, super, super tiny, bigger orbit? So let's print out the power of the sun, just for fun. Print P0 equals P0 watts. And now power is the work divided by the time. So the time is going to be work divided by the power. So let's say dt equals the work. No, see, it's power is work. I should have done this on paper. Power equals work divided by time. So time is work divided by power. All right, work divided by power. And that's in seconds. So let's see, print time equals dt seconds. Okay, let's run this. Oh, that's not too bad. 10 to the 3 times 10 to the 4th seconds. So let's say, how many weeks would that be? Let's just look that up and see. I don't want to, I can do it. Let's do it. No, let's do it. Oops, I messed something up. Oh, I crashed it. Okay, let's just do it manually. We'll do it live. Is this still recording? Yeah, okay. So let's say I'm going to convert this to weeks. And so I have seconds. I need to convert that to, I should do this on paper. Seconds converted to hours is dividing, I'm going to do it on paper. Okay, so here t equals 3.4 times 10 to the 4th seconds. I'm going to say I want to convert that to hours. 1 hour is 3,600 seconds. And then I need to convert the hours to days. So I can say 1 day is 24 hours. And I can convert that to week. I should just leave it like that. But 1 week, not a EK, AK, EK, WEK, is 7 days. So I need to divide by all that stuff. Okay, I'm glad I wrote it out. I tell my students to do that all the time. Write it out. Don't try to do it in your head. So I'm going to say divided by 3,600 times 24 times 7. And it'd be, okay, so it's a day. It's more, let's go back to days. Let's convert this to days. So half a day. Well, that's not so bad. Just use all of the energy of the sun, and it only takes half a day after you build the Dyson sphere. Okay, so what is the I'm trying to think, what is the power output of the whole sun? Well, let's say we capture all this energy from the sun at the Earth, and we use that to move it. Okay, so let's say P Earth, PE, is going to be the intensity at the Earth. And let's use the old intensity because we're going to save it up and then move, even that shouldn't make big of a difference, times the area of the Earth, right? So it's going to be pi r squared. So it's going to be pi times the radius of the Earth, which is, I didn't put down. Ooh. Okay, let's say REE. It's, what is the radius of the Earth? Is it 6.3 times 10 to the 6th? Erg. I hate forgetting stuff. Radius of the Earth in meters. It's 6.371. Okay, good. 6.371 times 10 to the 6th. So it's going to be times REE squared. And then I want to recalculate the power. Actually, let's move this up here. Let's just use that to recalculate the time. So dt equals W over PE. And let's run it. Now how long would it take? So now I'm not capturing all the energy from the sun, just the stuff that hits the Earth. And I'm assuming I have perfect solar panels and I have the whole half of the sun blocked up, the whole half of the Earth blocked up. Okay, so, oh, we didn't print it. Can't find IE because I can't type. It's IE. Okay, it takes a little bit longer. So it's going to take, what's that, 800 million days. Okay, so how about this? What if we scrap that whole plan? And instead of moving the Earth, we just use less energy. Or we produce less carbon dioxide. Or we produce no carbon dioxide. See, don't you think that's a more reasonable idea? I'm going to leave this for homework. How much energy, if you use, oh, I want to do that now. If you use 11 cents per kilowatt hour, which is the lowest energy that you could probably get in the United States, how much energy, how much money would it take to move the Earth? I'm going to do that, right? Because people respond to money. Okay, so let's say, let's call it dollar. Let's call it EP for price of energy equals 0.11 dollars per kilowatt hour. So I need to convert that to dollars per joule. So I could do that, but I'm just going to say 1 kilowatt hour in joules. I could do it, but I want to. So 3.6 times 10 to the 6. So this I say times 3.6. So that's cents per kilowatt hour. So if I want to convert that to cents or dollars per joule. Okay, let's write this out. Again, don't do it in your head. Okay, so let's say, what did I call that? EP equals 0.11 USD per kilowatt hour. And I'm pretty sure that's the right answer. And kilowatt hour is a unit of energy. Then I know that 1 kilowatt hour is 3.6 times 10 to the 6th joules. Okay, so I need to divide that by 3.6 times 10 to the, so that's going to be, go back over here. And that just shows you how cheap electricity is. Divided by 3.6 times 10 to the 6th. And now let's calculate the cost. C equals W times EP. Joules. Yeah. And that'll be in dollars. So print moving Earth cost. C dollar. Okay, it would cost 4 times 10 to the 23rd dollars. No one has that much money. The end. I think I proved my point.